This visualization captures the reality of modern medicine. What you are looking at are fragmented clusters of data, representing decades of scattered medical records physically disconnected from the patient they belong to. Your entire medical history, every test, scan, and treatment, is siloed in cold storage servers across multiple different network architectures. This creates the digital air gap, the severe physical and computational latency required to locate, fetch, and process a lifetime of information during a medical event. When you rely on standard server architectures, that lag makes it impossible to build a digital health twin, a real-time dynamic model of a patient's biology. To eliminate this delay, architects are targeting theoretical 2026 exascale benchmarks, like the Rodela framework. The operational goal here is to transition away from making diagnostic guesses based on isolated snapshots of old data, and instead continuously simulate a patient's biological trajectory over their lifetime. Hitting zero-latency clinical decision support requires rewiring the physical layout of the data center. You have to fuse direct memory hardware acceleration with strict constraint-based software into a single 4-layer stack. Layer 1 is the global data fabric, representing hyperscale cloud storage. Routing massive medical datasets through a traditional CPU stack forces slow translation, creating a massive traffic jam known as the von Neumann bottleneck. The solution bypasses the CPU completely. Specialized DPUs catch incoming data, routing it as a high-speed stream straight into the GPU array. DPUs take over the heavy lifting of networking, security, and storage tasks, unburdening the system. Because data flows directly into the GPU's high-bandwidth memory, the CPU never translates it. Achieving this hardware-level memory access is a mandatory prerequisite. Without DPUs closing that physical gap, real-time AI inference cannot exist. That brings us to Layer 2, the Agentic Core, running on advanced silicon like NVIDIA Blackwell. There is a persistent misconception that you can drop a standard conversational large language model into a hospital and get a reliable diagnostic tool. That approach is entirely unsafe. Clinical environments require a multi-agent system, where distinct, specialized AI models handle separate dynamic workflows autonomously. First, an administrative agent operates in the background, handling cloud coordination, cross-border compliance, and logistical routing. Second, a clinical agent, built on foundational weights like MedPalm or BioGPT, focuses exclusively on medical reasoning. But giving a clinical agent total autonomy introduces an unacceptable risk: model hallucination in life or death scenarios. To control this, we need Layer 3, the knowledge base, acting as an external constraint mechanism. In this logic flow diagram, you can see how the clinical agent's foundational weights are quarantined. When the model attempts to output a medical recommendation, the pathway is intercepted by a rigid external barrier labeled vector database. The system uses retrieval augmented generation, or RAG, to anchor the AI's logic strictly to a verified external source of truth. This constraint data comes directly from Aspet. The foundational model cross-references its initial guess against this vector database, recalculating based on strict pharmacology rules to ensure drug interactions are simulated safely before outputting a formatted recommendation. Separating the reasoning engine from the knowledge base using ASPET-constrained RAG is the only architectural method to achieve medical AI that operates autonomously without hallucinating. However, all this processing power must eventually reach the real world, places like rural clinics and mobile field hospitals. We cannot physically build multi-million-dollar exascale data centers in every remote location on Earth. That dictates the need for Layer 4, edge delivery. This generated schematic illustrates the division of labor. The heavy computational lifting, training models and compiling the longitudinal twin, happens up in the massive cloud server rack. That system then wirelessly transmits a compressed, refined algorithm down to a ruggedized small form factor terminal. These terminals utilize edge-optimized silicon, like Intel Gaudi or NVIDIA Jetson, to run the synthesized models locally. By pushing inference to the edge, this system guarantees zero-latency clinical support even offline. It democratizes access to diagnostic intelligence, bypassing local connectivity limits entirely. This 3D isometric diagram maps out the complete 4-layer architecture in action. Watch as a glowing data packet, representing a patient profile, enters Layer 1 in the cloud fabric and streams rapidly via a DPU straight into Layer 2, the GPU core. Tracking a simulated emergency, the DPU ingestion bypasses the CPU entirely. The packet hits the Agentic Core, where the administrative agent handles routing, while the clinical agent immediately pings Layer 3, querying the ASPET vector database. By referencing the patient's entire lifetime history against ASPET standards, the clinical agent identifies a hidden drug allergy. The ping returns green, validating the finding, and the signal shoots out of the data center down to Layer 4, the edge node. That validated therapeutic recommendation arrives at the remote edge device with zero latency. This pipeline replaces trial and error medicine with continuous, highly precise biological simulation. While the fully unified Rodela exascale framework stands as a benchmark targeted for 2026, the foundational primitives it relies on, DPU memory access, agentic workflows, and rigid RAG grounding, are the exact tools software and hardware engineers are deploying today. By restructuring how data flows and how models reason, architects are closing the digital air gap, establishing the necessary infrastructure